Hi guys, Dr. Musk back again, and now we're going to talk about section 16.6, which deals with weak acids and specifically what we call their ionization constants. So don't be afraid of the term ionization constant because all that is, an acid ionization constant is a fancy name for the Ka value for that acid. So we know what that is already. That acid's equilibrium constant. Now, for strong acids, those Ka values are huge, which is why we can assume that we get pretty much all products, H3O plus and the conjugate base, whenever a strong acid like HCl dissolves in water. For weak acids, we can't assume that because the Ka values for weak acids are small numbers. So you can see a couple of examples of Kas of common weak acids. CH3COOH, that's acetic acid, the acid that we have in solutions of vinegar. And then HF, the only one out of the halogen-based acids that's a weak acid. You can see their Ka values are both really small numbers. Now you can also see that the larger our Ka value is, the lower the pH. So that's only assuming that we have the same concentration of each one of those weak acids. So the larger our Ka value is, the stronger our acid. All right, and that's true for any acid. That's what Ka tells us. The larger its value, the stronger the acid is. But in general, weak acids have small Ka values. So that's a big difference in terms of how we're going to use those acids to calculate a pH of a solution. Now here, really quickly, are some Ka values for a number of different weak acids. There are, there are entire tables of 20 or 30 pages that have nothing but different acids and their Ka values. So if you want to look up a table full of those, the Evans Ka table or the Evans pKa table, which is just a different way of talking about Ka values. The negative log of the Ka is the pKa. So the Evans pKa table is many, many pages long, and it's something, a reference that chemists all over the world use when they want to refer to the relative strengths of different kinds of acids. Now, really quick, let's take a look at how we calculate the pH of a weak acid using its Ka value. All right, remember that for a strong acid, if we know its concentration, we automatically know its concentration of H3O plus because the H3O plus concentration is the same as the concentration of the strong acid. With weak acids don't completely react with water, so we have to use their Ka expressions to be able to find the final concentration of H3O plus at equilibrium. Here's a quick example, all right? Assuming we're trying to find the pH of a 0.5 molar hydrofluoric acid solution. We start out with a 0.5 molar concentration of HF and none of our H3O plus or F minus. To get to equilibrium, we're going to have to react some of that HF with water, and since there's a 1 to 1 to 1 mole ratio of HF and H3O plus and F minus, whatever concentration we lose of HF, we gain of both H3O plus and F minus. So at equilibrium, our final concentration of HF is 0.5 minus X. Our final concentration of H3O plus and F minus are X. Hopefully you guys are good enough at equilibrium calculations to already be able to set a problem up like that by yourselves. So then we just have to plug those equilibrium concentrations into our equilibrium expression. And we can probably assume that because HF has a very small value for its Ka, 7.1 times 10 to the minus 4, let's go ahead and make the assumption that 0.5 minus X is approximately equal to 0.5. So X squared then would be equal to 0.5 times our Ka value. So X squared is equal to 3.55 times 10 to the minus 4, and X would then be equal to 1.9 times 10 to the minus 2. Notice how we've defined X. X is our equilibrium concentration of H3O plus. So because of that, we can take the negative log of that to find our pH. So since that is our equilibrium concentration of H3O plus, negative log of H3O plus equals pH. All right, let's just check and make sure that our change wasn't 5% or more of our starting concentration. So there's our X value divided by our starting concentration times 100%. It looks like we're still passing the 5% rule, although it was pretty close this time. So we made a good assumption in ignoring that X compared to the starting concentration of 0.5. So let's look at one more calculation for how we can calculate the pH of a weak acid solution. This is a core skill. I expect you to be able to do it. All right. All of us have done this equilibrium math, so I'm not going to spend too much time on how we set this problem up, but then we plug back into our equilibrium expression and get x squared divided by 0.0075 should be equal to our Ka, 3.5 times 10 to the minus 8. So you can see that when we solve for x, we get that molarity of H3O plus. We've defined x as our equilibrium concentration of H3O plus, so we could take the negative log of that value to find the pH of the solution. So think about it, go ahead and pause for a second and read through this, all right? This is just our way of tuning our BS detectors to make sure that our answer makes sense, all right? And if you notice, when we put in our initial concentration of H3O plus into these calculations, we use 0 molar as our initial concentration, even though we know that pure water has a molarity of 1 times 10 to the 7th molar. We're just neglecting that small concentration of H3O plus to start. It's not going to make that big of a difference, all right? So another way that we can talk about the strength of a weak acid is to think about what percent of it is reacting with water. That's called percent ionization. So the way that we do that is to find our percentage of H3O plus compared to our starting concentration of the weak acid times 100%. All right, that's the fraction, that's the percentage of our weak acid that is chosen to react with water. So if we look at this particular weak acid, so C6H5COOH, that's benzoic acid. And if we solved for what percentage of a 0.1 molar solution of benzoic acid actually reacted with water, then in the end, we're going to find that about 2.5% of it reacts. So how do we do that? Well, we have to know the Ka for benzoic acid. You could look that up in the Ka table just a few slides back if you want to. All right. And then once we solve for our final concentration of H3O plus, we can compare that to our starting concentration of the benzoic acid. So our H3O plus concentration divided by our starting benzoic acid concentration times 100%. That's what gives us percent ionization. So if we have a strong acid, essentially 100% of that strong acid ionizes no matter what the concentration of the acid is. For a weak acid, the higher our concentration of the acid, the lower the percent ionization. All right? So go ahead and take a few minutes and work through this problem with me. So let's figure out just A together, all right? And if you want to, you can do part B and part C, but we'll just do A together, all right? We can do an equilibrium table, and then we're gonna solve for our final concentration of H3O plus in an acetic acid solution. Remember, acetic acid has a Ka value of 1.8 times 10 to the minus 5. So if we solve for our final concentration of H3O plus in that 0.15 molar acetic acid solution and compare that to our starting concentration of acetic acid, that's what's going to allow us to find percent ionization. So here is the solution to part A. We did our little ice table, And then we calculate by substituting back into the equilibrium expression. So Ka is equal to H3O plus times acetate divided by acetic acid, products over reactants, just like always. We know the value for Ka is 1.8 times 10 to the minus 5. So 1.8 times 10 to the minus 5 should be equal to x squared divided by 0.15, assuming that we're neglecting that small x in our approximation. So if we solve for x, that should give us 0.0016 molar for our final concentration of H3O plus. If we wanted to solve for the pH, we could take the negative log of that. But what we're interested in is what percentage of the acetic acid ionized or split apart in water. So here is the part of the acetic acid that turned into H3O plus. So that's our H3O plus concentration divided by the starting concentration of acetic acid. And then we multiply by 100% to get our percent ionization, 1.1%. We can also use the pH to determine a Ka value. All right, so imagine we have a weak acid that we know its concentration and we know the pH. Using those two things together, we can calculate a Ka value for that weak acid. So here's how we do it. If we know the concentration was 0.25 molar of the weak acid, that was our initial concentration. We also know the pH, which means if we know the pH, we also know or can find the H3O plus concentration at equilibrium. So our H3O plus concentration at equilibrium is the negative log, or sorry, the 10 to the minus of that pH. So this is 10 to the minus 3.47. And I just did the calculation to turn that into proper scientific notation. Now, because we know that for every molarity of H3O plus at equilibrium we have the same molarity of A minus. If we know this number at equilibrium, this one has to be the same thing. So let's plug in what we know about the equilibrium into the equilibrium expression, and we should be able to solve for Ka. There's our final concentration of HA at equilibrium, and here are final concentrations of H3O plus and A minus. So our Ka should be equal to 3.39 times 10 to the minus 4 squared divided by 0.2497. Now note that I did subtract my x value from my starting concentration here. If you just substituted 0.25 into the denominator there, you're going to get the same value for Ka. It's not significantly different because of the small x approximation. So whether you want to use 0.2497 or just stick with 0.25, most of the time, not subtracting out that small x, as long as x is tiny, is not going to make any difference at all here. So once we substitute in and solve, we should find a Ka value of about 4.6 times 10 to the minus 7. I'm going to let you guys work through the last example together by yourselves, but this section just teaches us how to use that Ka value and how to use final concentrations of H3O plus that we can already find through doing good equilibrium math to solve some problems related to weak acid.